Hey everybody, Mr. Adamson here. Welcome to another lesson in Biology 30. This is part of the population ecology lessons. And in this little instructional video here, you're going to learn about calculating population density, population growth rate, and per capita growth rate. So the first thing that we're going to start with here is how to calculate population density. Now, just to give us some definitions, we have population density right here is the number of individual organisms in a given area or volume. And just key, you can't have area or you can't have volume, which will be indicated by either area here with the A or volume here with the P. So either or formula is going to be acceptable. When we look at the formula here, we have population density, so dP equals N. N is our number of individuals or number of organisms divided by A, or this could be V in this example. And again, if you want to actually calculate though the number of individuals, manipulate your formula where you will have density. You have to take A here to the other side of your formula, or V, and you would get number of individuals equals density times the area or volume. So just to get right into how to calculate this, just some examples of calculating population density. If we have, again, our formula is D, or population density equals N over A, or again, it could be dP equals N over V. So if we look at example number 1 here, we have 44 students. That would be our number. Our area is 100 meters squared, and therefore if we go 44 divided by 100, we get an answer of 0.44 students in a meter squared area. You have 12 gophers. You have an area of 10 meters squared. Again, 12 divided by 10 gives you an answer of 1.2 gophers per meter squared. And then if we go to this formula here and we use a volume, we have 54 minnows. We have a 200 milliliter, say, fish tank. We divide our number of minnows by our volume, and we get 0.27 of a minnow per milliliter. Now, I mean, that's not actually possible, but to give you the actual correct statistics of how many minnows within that area, that's what population density does. All right, what we have here now is old diploma exam question. So this will typically be a question that you would see in relation to calculating population density. So it's not going to be straightforward like you saw in the previous examples I gave you. I mean, if you're lucky it will be, but more likely you're going to see questions that are very similar to what I've pulled for you here. Now, information you have is, you have some information for Jasper National Park in Northwest Territories. And you're given either Animal 1, Animal 2, you're given density of predators. So in relation to Animal 1 and 2, you're talking about the wolf population, and then you're also given the number of prey that you have. So if we go back to our formula, we have population density equals N over A, or population density equals N over V in volume. But we are dealing with areas here, you can tell, not volume, so we're not going to deal with that. Now the other thing that we need to be cognizant of is, do we need to manipulate our formula? What are we being asked? Well, if we go down to the question here, the size of the wolf population in an area of 6,000 kilometers squared, so we have an area of the Northwest Territories, is calculated to be 18 wolves. So you have the answer there right now. What does 18 represent? It's the size of the wolf population. That represents our number. So you have to figure out though first how to get, you're not actually given that number, you have to calculate that number. So we have to rearrange our formula to find N. And to do so, we have to get A to the other side. So we multiply each side by A, cancel it out on the right, and you would get our number of individuals equals density times the area. Now, it's not just straight simple thing as taking our numbers. So our area is 6,000 here. So if I represented 6,000 for A, and my density, because again, we are looking at the Northwest Territories, so we're looking at this value here, 0.3, because that is going to equal 0.3 times 6,000 is going to equal 1,800. Now, what is wrong with that? Now, a lot of students, they'd probably get that, but I mean, a couple things you got to consider here is we are looking at an area of 6,000 kilometers squared, and our D value, though, is only per 100 kilometers squared. So what do we have to do to this value here, our number of individuals, because it's per 6,000, we have to get it down to 100 kilometers squared. And to do so, we divide by 100, and therefore we will then get 18 wolves in 100 kilometers squared area, or a total of 6,000 kilometers squared area within the Northwest Territories. So I hope that makes sense. The big thing is when you're working through this question here, make sure that all your values are on the same plane, meaning if you're asked to find something within 6,000 kilometer squared area, but you're only given information that say is in 100 or 200, bring all your numbers so they're represented within the same sample size. Now, why do we need to calculate population density? So if you know your community size, you can now estimate the size of your population. So examples, in our school, if we have 1,000 meter squared area, and we know that we have 4.4 students in that area, we could calculate that we have 4,400 students within the area. On a field, if we know the size of our field is 200 meters squared, and we know from previous examples if we have 1.2 gophers per meter squared, we just multiply by our size of our area, and we know that we probably have 240 gophers. In our fish tank, if we have 2,000 milliliters, or maybe you're given 2 liters, but again, remember, we were calculating before in previous example with milliliters, we have to bring it back to the same thing, calculate what we found for density, times our area, and we would get 540 minnows. So this is just another example of how you can manipulate that formula and kind of work your way forward to figure out if you know specifically what you have within an area, you can make it bigger and guesstimate what you have for an even bigger zone. So just a bit of population density practice here. You have a fish tank that is 10 meters long, 5 meters tall, 2 meters wide, and it's filled with water. Now the population density of the bacteria in the water is 1.5 times 10 to the 4th bacterium per meter squared. Approximately how many bacteria are within the fish tank? Well, if we go through this, and just to show you, we need to first calculate the volume of our swimming pool. Our volume is 10 meters times 5 meters times 2 meters, which gives us 100 meters squared. So that equals our volume. Now the population density already what we're given is 1.5 times 10 to the 4th bacterium per meter squared. Therefore, the population density of the bacterium in the water is represented by a formula which we will need to manipulate. So going from our original formula to this, like we did in the wolf question, and we will get our value for density times our volume, which would equal roughly about over 100 million. Take that back to scientific notation because we need to be cognizant of scientific notation, and we would get 1.5 times 10 to the 6 bacteria total as our number within that volume, and if we have calculated a density per that volume. So just to give you another diploma type example question here, swimming pool is 50 meters long, 20 meters wide. Okay, it's filled to a depth of water of 3 meters. The population density of the bacteria is 2.5 times 10 to the 6. So what do we need to do? Well, first we need to figure out what is our volume. Well, we take 50 times 20 times 3, which is going to equal 3,000. So that is our volume. We already know that our population density is 2.5 times 10 to the 6th. We have rearranged or manipulated our formula, so our number is going to equal dP times V, we multiply this value times that value, multiply, and we will get an answer for n to equal 7.5 times 10 to the 9 bacteria. Now, population density, is it always 100% accurate? So note that you need to know how a population is distributed within its habitat before taking samples to determine the population size. So some populations tend to be clumped in certain areas, which can affect the accuracy of your estimation. So I mean, if we are looking at two different samples here, so we could have a whole bunch of bacteria that are clumped within that area and maybe clumped over with another area here. And if we were to break apart and grid, you would not actually, this would not be an accurate calculation, because as you can see, we have nothing within this square, we have very little in this square, very little in this square. So I mean, our population density calculations would be slightly off because they would be clumped. However, if you know that your populations, okay, are very uniform within their spacing, within your area or volume, your population density calculation would be a lot more accurate. So it is important that you know how are they distributed within their habitat before you carry out the population density calculations. Now, a couple other things that we're going to talk about here is growth and regulation of populations. So next one is population growth. How do populations go up or go down? So a population gains individuals by natality, which is a birth, and immigration, so new individuals coming in. Population loses individuals by mortality, which is our death rate, and emigration, so individuals who move away or leave. Now, the balance between these factors will determine whether a population size grows, declines, or remains the same. So, to calculate change in population size, we have the formula: change in n equals the factors that increase a population minus the factors that decrease a population. So although this formula is given to you, you should know that, I mean, the factors that increase population, again, are births and immigration, and the factors that decrease population, so these ones here and those ones there, are death and emigration. Therefore, just to kind of break it down further, change in n, or population size, equals births plus immigration minus deaths plus emigration. Now, to calculate the change, say, of a sandhill crane population at the Banks Island breeding site in 1991, we had a birth rate of 40 individuals. Our immigration was 0, so no individuals are moving in. We had a death rate of 55 individuals. We had an emigration of 0, so again, nobody was moving out. And our initial number was 200. So what is the importance of this number here? Well, first, let's figure out what is our change in n. So if we get our formula here, we have 40, again, which is our birth. Immigrants are 0. We have 55 with immigrants 0. And we get a change in n of minus 15 individuals. Again, what is the importance of this 200? Well, we'll come to that, but first what I want to do is look at this question, and we'll swing back to what we just did. So if we look right now, we have the red-winged blackbird's adaptability has allowed it to become one of the most abundant birds in North America. So this is some information. Again, this is a diploma type question that you would see. So we have a study of red-winged blackbird nesting sites. So the initial population of the red-winged blackbirds is 208. In year 1 of our study, we had 22 births. At the end of year 2, we had 43. We had very little deaths the first year, a couple more the next year. Birds entering, so immigration was 0 the first year. We had 2 immigrate the second year. We had 2 emigrating the first year, and we had 5 emigrating or leaving the end of the second year. So the question is here, at conclusion about this nesting site study, is that red-winged blackbird populations increase because, well, first thing that we need to do, so if we just kind of look here, let's move this up. we have already given your answer. So natality plus immigration exceeds mortality plus emigration. So I mean, if we look at that right now, if we have births, we have 22 our first year and 43. That is substantially higher than our death rate, which is right here. And we have, I mean, immigration and emigration. These numbers aren't very different. I mean, we have 2 total and we have 7 total here, which is a difference of 5. But we have a substantial difference here of our birth rate. 22 plus 43 is 65, and this is only 11. So that's a substantial increase in our birth rate. So we can see that natality, our birth rate, plus immigration exceeds, so this 65 plus this 2 is greatly exceeding the 11 plus this 7. We can cancel out B because mortality plus emigration exceeds natality. No, it doesn't, because 11 plus 7 is not greater than 67 total. Natality plus immigration exceeds mortality. Well, that's not even how we calculate population growth. And mortality plus immigration, again, that is not how we calculate population growth. So we come back to an answer of A here, because 65 plus 2, which is 67, is greater than 11 plus 7, so 18. Therefore, natality plus immigration exceeds mortality plus emigration. Now, the percent population growth. So this is where we're going to circle back to our original question that I had talked about here in relation to the sandhill crane. So this formula is not given in your data sheet, but it's quite intuitive and very, straightforward. So recall that the change in population is represented by the change in N equals births plus emigration minus deaths plus emigration. So therefore, percent growth, so our change in population, which is N, which is what we are calculating right here, divided by our initial population times 100. So if we go, we can also break it down, because we know that change in N equals births plus immigration minus deaths plus emigration. So if we go back to our original question with our sandhill crane here, we can forget about immigration, emigration, because both of those values were 0 right now. But we had a birth rate of 40, we had a death rate or mortality rate of 55. So therefore, we had an answer which came to negative 15 individuals. So our population went down, but our initial population of the sandhill crane was 200, which is right here. And we times that by 100 to get a percentage value, and we will see with our sandhill population, our crane population, we had a negative 0.75% decrease of individuals during the year 1991. Now, population growth rate. So this is the change in number of organisms in a population per unit of time. So you can see here, our growth rate equals the change in N, so our change in populations, over change in T. T again equals time. So the rate of population growth does not take into account the initial size of population. So a large population has more individuals that can reproduce compared to a small population. So to compare populations of the same species that are different sizes or live in different habitats, the change in the population size can be expressed as a rate of change per individual. This measurement gives us a per capita growth rate. And so this is a value that we are also going to be, that you're going to need to know how to calculate. Now, the per capita growth rate can be calculated by using the formula CGR equals the change in N over N. So CGR is the per capita growth rate. Change in N is the change in number of individuals in a population. So again, with the emigration and the natality and the death rate and the emigration, and N is the original number of individuals within the population. So why measure per capita growth rate? This is to examine the population size as the rate of change per individual. So suppose that in a town of 100 people, there are 50 births, 30 deaths, no emigration and no immigration. Calculate the per capita growth rate. Well, to do so, we have to take our change in N, which is 50 births, minus the death rate, which gives us an additional 20, a difference of positive 20 people. Our original number of people was 1,000. Put those into our formula. Here's our 20, here's our 1,000, and we get a per capita growth rate of 0.02. So could the answer be a negative value? That's a great question to ask. And the answer, very straightforward, is yes. Let's say if we just change these values slightly here, and we go 30 births, 50 deaths, we now get a negative 20 people, because we have, negative people coming. Sorry, not negative people coming, but we've gone down by negative 20 people. So we have this value here, of negative 20, and we would get an answer of negative 0.02 people, which means our population is going down by per capita by 0.02. So just to give you another diploma type question on what you would see on a diploma exam, you have a question here about snow geese nesting near Churchill, Manitoba. So before you read all this information, it's always wise, look at the question. What are you being asked? What do you need to really look at and pull out? So based on the information above, what is the per capita growth rate of snow geese population between 1968 and 1990? So that's a 28-year difference. So we are looking at per capita growth rate, or CGR. So we know that we need numbers. That's what's important in this question. So we have in 1968 to 1990, the population of snow geese went from 2,000 pairs, or 4,000 individuals, to about 22,500 pairs, or 45,000 individuals. Now, it's important, if you're going to calculate this, stick to the pairs. So use this value for pairs and this value for pairs. Or if you're going to use individuals, use this and this. So first thing we have to do, what is our CGR formula? Well, CGR equals the change in N over N. So what is our change in N? Well, our change in N, if we stick with the pairs, we had 22,500 pairs, and we went up by, we started with 2,000 pairs. That's going to equal a value, sorry, I'm running out of room here, of 20,500 individuals. So that is our change in N. That's how many geese that we went up by. Now, just to move this here, we then need to calculate our N. Our N already we know was our original population, which is 2,000. So therefore we take 2,500, which is our change in N, divided by our original population, and we get an answer of 10.25. And if you look here, record your answer, rounded to one decimal place, 10.3, which is the same answer that we have here. So again, that's an example of how to calculate per capita growth rate. All of the rest of the information within this question here would just be as a distractor to throw you off. So again, it's important. What are you being asked within the original question down here? So that is just some examples on how, when you're working with population ecology, how to calculate per capita growth rate, how to calculate the population growth, and then how to also calculate population density. I hope that made some sense to you. Hope you can get some practice in. If you need to, rewatch certain sections. But thanks for listening, and hope you enjoyed.